and that way everything we do will be here. I do have a new toy. It's a Wacom thing that you write with, and it's a lot better on the whiteboard. So hopefully that'll go a little faster today. I'm still not used to it, so I'm still a little rusty on it, but it worked okay yesterday. As I get better, more used to it, I'm sure it'll get a little better. So if you don't have any questions, let's go on and get started. We are recording, and here is the text in front of us here. So we're starting today, or at least my memory was, we're starting on 2.6 numerical method, right? Is that your remembrance and understanding? Okay. 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 And I did put out there the test. Someone had asked for it last week. Didn't get it as soon as I wanted to because I had all these administrative things that came up over the weekend that I got bogged down with, and still have a bunch hanging, but I did finally get it out there. Until we finish 2.6, you can't do all the tests, but you can at least get started on the first part if you want to. It's a fairly long test, but I hope it's not as intricate as the last test was. Some of those problems were just way too, took a lot of time anyway. So this one is a lot to it, but more of it is just identifying which method you would use, okay, or which method it's a problem is qualified for. All right, so if there's no questions, let's go on and get started on numerical methods. They started the chapter talking about qualitative information on first order differential equations, and then analytical information on first order differential equations. Okay, now, analytical solutions means we actually find a way to solve them. Okay, qualitative information, that was sort of like the directional things that we had, you know, just giving an idea of where the differential equation is going. In this section, and here's the issue, but a differential equation can possess a solution and yet may not be possible to obtain analytically. This statement right here, okay? In fact, I think in real world situations, most of your differential equations, number one, you probably can't pose them precisely because they're really complicated and complex systems. Okay, for instance, I had a professor one time who was trying to describe the weather as a system of, I don't know if he got into differential equations, but as a function. And when he put all the function things down there, it was just overwhelming. You know, temperature, pressures, moisture content, wind speeds, you know, at different elevations, you know. By the time you got everything on there, you had a function of, I don't know, I'm just going to guess 10 variables, okay? Yeah, okay, something like that. If you're trying to model that with a differential equation, that's all you're going to do is model. You're not going to come close to solving it, okay? So that's the issue sometimes. So, but even if you could specifically pose the problem as a differential equation, then it may be that analytically there's no technique that will work exactly, okay? So you either start making approximations, and there you get into qualitative sort of things, you know, analytical but qualitative. But we finish this chapter to round out the picture of different types of analysis. We conclude with solving, in quotes, a differential equation numerically. Okay, now this is just going to be one method. It was a fairly early method. It's not a very precise method. Nowadays they have computer packages out there that will basically do anything you want. But this is a course on how to use a computer package, okay? Probably when you get to your job or whatever, and if you ever need one, your work will have their favorite computer package, probably because it's going to be a differential equation, if you ever run into one, that they deal with all the time, or one similar to one they deal with all the time. So you'll learn basically the numerical technique or the way to use the package to come up with approximate solutions. And again, approximating the unknown solution. That's the deal here. In this section, it's really an approximation, not a particularly good one, but at least it's a decent approximation. Okay? More extensive treatment of numerical methods is in Chapter 9. With this short summer term that they've shortened even more, I doubt if we're going to get to Chapter 9. So this is going to be our approach to numerical methods. That was in your course description. It'll just be this. So let's assume we have a first order initial value problem. Y prime, oh, here comes Billy. Okay, now I put everything down here, but I forgot to mark you present, Melissa. Okay, I got the dates down and everything else, but let me get both of you, let me get rid of the stack of papers here. All right, Melissa's here, and my pen just decides to write sometime and sometimes it doesn't. And then Billy just came in. Now I saw Corbin's name earlier, like I said, before I'd even started the Zoom, but now I haven't seen him since we've been doing Zoom. So, and now I can't see Billy. Okay, there she is. Yeah, I see you now. Okay, gotcha. Okay. Melissa had been in that black box and she disappeared, but you showed up. Okay. Okay. And like I said, no, it wasn't Corbin. It was Cole. Cole. Hey, here he is. Okay, Cole is here now. All right, or at least he's coming in. All right, Cole, are you in yet? Yes, there's Cole. Cole, I saw, just because Zoom sends a message, you were here way early this morning, but then when I got the Zoom was very, very, very slow opening this morning. And by the time it got open, I couldn't see you anymore, but I'm glad you hung around. What's that? Okay. All righty. Well, let's go on from there. When Melissa and I got started and we were talking about the beginning of 2.6 numerical method, the fact that a lot of times you'll run into a differential equation that either you can't solve analytically or maybe you can't even pose it analytically in a way you could solve it. So you do your best with a numerical method. And this is using the tangent line. So here's your first order initial value problem. Y prime is equal to some function of x and y. Okay, that's, what did they call that? The normal form for expressing a differential equation, first order differential equation. Now, you have an initial value. Y of x0 is equal to y0. That's pretty standard. Okay, the problem may be there's no technique that will solve this. Okay, linear doesn't work, separation of variables doesn't work, numerical exact doesn't work, Bernoulli doesn't work, homogeneous doesn't work. Nothing seems to work. Okay, but let's say it does have a solution. Okay, you know you ought to be able to get there. So one way of approximating a solution is to use tangent lines. Okay, now remember way back first when we did that qualitative stuff, the tangent line indicated the direction your derivative was going, positive, negative, whatever, at a certain point. So if you know this is a starting point, that the situation, whatever you're modeling here, is going to be when x equals 0, you're going to be at y0. Plug those values in right here for your f of x, y, and that gives you the slope of the function. So not only do you know where you are, but you know basically which direction you're heading. Okay? So, let's let y, okay, sorry about that. Too too many things open at once. Let me scoot this up some. Get all that verbiage off of there. Okay. Now, I think I'm going to move Cole. He's in the way. You're always in the way, Cole. Okay. Let me move you up here. Okay. All right. Over just a tad. Okay. We'll assume this does possess a solution. For example, let's let that y of x denote the unknown solution for a first-order differential equation such as this. Okay? Now, just looking at that, do you think you can separate the variables? The answer is no, because you got a plus sign here rather than times sign. Times sign, yeah, you'd be able to do it. Okay? Linear, definitely not. The square root of y, no way linear. Okay? Let me go through them all. Exact, don't think that's going to work either. Okay? Don't believe that's going to be able, even if you come up with a adjustment to it, still not going to work. Let's see, what were some of the homogeneous? Nope, no way. This is power to the 1/2. This is power 2, not going to work. Let's see, what were some of the others? Bernoulli, no, don't believe so. None of the methods right off the top looks like it's going to work with that. Okay, so that's a nonlinear differential equation. That initial value problem cannot be solved, not that we don't know how, cannot be solved directly by any of the methods considered in 2.2, 2.3, 2.4, 2.5. However, we can find an approximate solution of the unknown function y of x. Okay? Now, let's say we'd like to know what it is when x is equal to 2.5. Okay? This could be an optimization problem. It could be, what is your output going to be at a certain time, whatever. So you want to know 2.5 hours from now, days from now, years from now, whatever. Okay, you're going to try to find 2.5. You know what your initial situation is here, and this is what you're going to be undergoing here. Oh, there it is. Y of 2 is equal to 4. I forgot that. So we know we're starting when x equal 2, y is equal to 4. We want to know what's happening when you get to x equal 2.5. Okay, now that does have a solution, and the flow in the direction field, which we did before when we were just doing qualitative, the solution curve must have a shape similar to the curve shown in blue. Let's see if we can get that to show up here. Here we go. All right, we've lost our equation, but we'll come back to it. So here we're, get a little bit further down here. Okay. Okay, here's the direction field. And what they did, they plugged in ordered pairs, x-y pairs, and certainly when x was 0 and y was 0, the direction, the slope was 0. When x was a little bit greater, like 1, but y was still 0, then you had some slope, a steeper slope here, slope back here, steeper here. Symmetric kind of, the slopes anyway, about the y-axis. But as you go up in y, then your slopes tend to increase just a little because that's the square root of y. Okay? And they tend to do like that. If x is 0, then you're only dependent on that square root of y function, and those slopes are increasing very, very slowly here. Okay, but if we're starting at 2, 4, when x equal 2, y is equal to 4, you're right here, and there you're in a pretty good slope field here. This is indicating that. We're going to go back and see how they got this slope of 1.8 in just a minute. But that's where you are. Where are you going to go by the time you get to 2.5? Somewhere over here. Okay? That's going to be our issue. Okay? So what I think I'll do is go to the whiteboard. okay? And at the same time, see if I can get my Wacom to work. For those who came in a little bit later, I was telling Melissa that I got a new toy. One of my other math instructors told me about it, or sent me information about it, and I passed that on to my wife. She looked into it, found it online, ordered it. It came in last week, and we got it loaded over the weekend. It's another reason I couldn't get as much done over the weekend, because we were trying to get this to work. So let's see if we can get it to work. Let's write down what our problem is so far. Okay, now try to set this on my computer thing so I can see, be writing here. See, here's my pen now, and I can go anywhere on the board, or pretty much anywhere. Okay, so here's the situation. Y prime, which by the way is dy dx, you know that, okay, is equal to 0.1 times the square root of y. And now this I don't understand. Every now and then it goes to some sort of a text box here, and I have to go back to the write mode. I've got to figure out why that happens and try to avoid it. Square root of y, okay, plus 0.4 x squared. Now this is a little bit better than writing with my finger of my right hand. Do you think so or not? Yay or nay? Do you like it better than what we were doing, or you rather go back to the old? Initial condition, y of 2 is equal to 4. It's easier on me anyway, so if y'all don't have an opinion, we're going to go with it. If you do have an opinion, let me know. Okay. Now, what we want to know first is where do we begin? Okay. Well, we begin by saying what is the slope, your first derivative, when you plug in this initial condition. Okay. So let's do. I'm going to call this, like the book does, m, but I'm going to call this the m at the point 2, 4. When x equal to, y is equal to 4. What is the slope then? Well, that is 0.1 times the square root of 4, which is 2, plus 0.4 times 2 squared, which is 4. Okay? Well, 0.1 times 2 is 0.2, plus, and 0.4 times 4 is 1.6. So your slope there, another thing it does sometimes is just dings and doesn't draw. Okay? So that's 1.8. Okay, so that's how they got in the text the first thing. Your slope there is 1.8. Now I'm trying to find where we are in the book. This is the top of page 77 in the first full paragraph there. It says direction field blah blah blah, and that gives you the slope of 1.8. Exactly what I just did. Okay. Now, from that point, I think I'll move my book to my lap here and see if that will help any. Now, hate to be going back and forth, but I think I will. Yuck. That's the other thing I haven't gotten used to. I have this on my keyboard, so I go to move my mouse, and it doesn't move because it's not my pad. So let's go back here, and let's see, what we've just done was determine f of 2, 4 is indeed 1.8, and that is your slope at that point. Okay, and that's why right here at that point 2, 4, you see your slope field is a 1.8. Now at this point the slope, the curve seems to be, at least in this drawing, very close to that linear approximation. You know it's not. You know it's not exact because this is a curve here. It's not a straight line, but it's a pretty good fit. Okay, so what they're going to do now is let's let using that point and that slope and the point slope formula for a line, we have that y, this is an approximation for y, is equal to that linear approximation of x. Well, what is that linear approximation? It's 1.8x, that's the slope, plus, and then they came up with this 0.4. Now, what they did here, okay, is when you, let's see, okay, they don't describe where they get it from here. But what you do is this. Well, let me go back to my screen. So I'm real tempted to write on the page there, but I'm not sure Wacom will do as well there. Okay, what we have a equation. Okay, this is the linear approximation, what they're calling L of x. Whoops, I'm so used to my old thing, I was trying to write on the screen. Okay, let me get it here in place. Your L of x, which is linear approximation of x, we just found to be this thing right here, 1.8, there's the slope. Okay, let me back up just a bit. Okay, all right, well, I thought I hit the eraser thing, but it didn't take. There we did. Okay, so let's wait on this just a moment. Okay, let's go back to our draw mode. There we go. This I point to the thing, gets right on it, and when I hit the thing it moves, so I don't know why that happens, but anyway, so here's the approximation. We have a slope. This is now our slope, and here's your slope intercept form. Okay, I hope you remember this. Y, not slope intercept, point slope form. Y minus y1, this goes way back, is equal to, and again they don't draw equal signs well, m times x minus x1, right? Yuck, this is ugly. Now, part of the reason for this, I'm writing with my left hand, but I don't know if you know how left-handers quite often do. I usually write like this, but on this board, then I'm pressing down on buttons that make all sorts of things happen. So I'm having to write like this, which is not how I'm used to writing. So that's why the pen does weird things. I'll get better at it, I hope, with time. Okay, well, here our x1 and y1 are your, come on, 2 and 4, and your slope is your 1.8. So let's plug that in here and do y minus 4, that's the y value, is equal to m times x minus 2. That's your initial value for your point value for x1. Okay, let's work that out, and you get y minus 4, we'll leave that as minus 4, is equal to, oops, why didn't I write that down? 1.8, I should have written that rather than m, times x minus 1.8 times 2 is 3.6. Okay, now we're going to add 4 to both sides. okay? And this gives us y, which is your linear approximation of x, okay? Because this is a linear approximation now. Now it's exact at this point, but not going to be exact other places. 1.8x, goodness, that's ugly, plus 0.4. Sometimes it pulls a line from somewhere, so I'll put that a 4.0 so it's clear. That's how they got sorry, I'm pretty slow at this, having to move back and forth between the two. That's how they got this equation here, okay? That's your linear approximation, y or L of x, the linear approximation where it's going at that point, 1.8x plus 0.4. That's how we got it. Last equation is called the linearization of y at x equal 2. It can be used to approximate the values of y in a small neighborhood of x equal 2. Somewhere real close to x equal 2, like slightly more than x equal 2, that's going to give you a really good approximation, the red line, of what the blue line is going to be, if you're a small enough approximation. That's the key, okay? Small neighborhood of x equal 2. If y1 then would be L of x1, denotes the y coordinate of the tangent line at the point y of x1. Now x1 is not the same as x0. It's another point, okay? It's going to be close to x equal 2, but not quite. Then the y of x1 that you get from this formula here, okay, when you plug in an x1 here, that gives you a new approximation for y1. Probably not going to be exactly the same. In fact, it's not, ever, okay? But it's going to be pretty close, okay? So, if that x1 was 2.1, say, so choosing, they're going to talk about this later, that's called your h, your step size. You're going from 2 to 2.5. Remember, that's what we're trying to do. It's already off the screen now. We were at 2, and we know the value there is 4, y value. We know that one. So what if we go a little bit further, like 0.1, 2.1, and with this approximation, see what the y value will be then on the tangent line, hoping that's going to be close to what it is, and it will be close to what it is on the slope line, on the actual curve, the blue line, okay? And that will give us a new approximation, y1, which is not going to be exactly the same as your y of 2.1 from your whatever your solution is, that curve, but it's going to be pretty close, okay? So let's go and do what they just said. Go back to our whiteboard. Okay, so let's plug in the, we've already done this. This is your linear approximation. So to get y1, let me get my board back here. Okay, where's my pen? There's my pen. Now, this is different in that I'm used to, on the keypad, moving around. This is always in place. So y1 is going to be 1.8. Well, see there, it does that again, and I don't know why it does it. Okay. I'll get better at this later, but I'm not good now. So there, it's done it again. Okay. There's something about my holding it in position too long, or pressing too hard, or not hard enough, or something. Okay. 1.8 times, now we're going to use 2.1 as our value, plus 0.4. Okay, using what we had before, okay, this will give us Now it's time for my calculator. I'm not going to do all these in my head. Okay. All right. And hopefully you know your calculators well. 1.8 times 2.1, the new value for x, plus 0.4 equal, that gives us 4.18. Okay? And that's what they had in the text, 4.18. Okay, 4.18. At 2, it was 4. At 2.1, just a little bit further, the approximation is 4.18. Okay, so that's how they got this part. Now, oh yeah, trying to find my cursor. There it is. Okay, so let's go back here. And that's how they got 4.18. That's our approximation. Okay, now, what we're going to do now is something called Euler's method. And if, by the way, you haven't chosen a paper topic yet, oh, good old Leonard Euler would be a good topic in just about any field of mathematics. Differential equations, linear algebra, calculus. He was all over the place. He was one of the most prolific writers of mathematics ever. Okay. He and Gauss, I think, were both. Gauss actually did more math and physics. Euler, though, I think he holds the record for the most number of publications ever. Okay, and this was back before word processing, before computers, before anything. He was able to develop so much in so many fields. Seldom been a mind like this. Believe it or not, he actually lost vision in one eye. I don't remember if it was disease or an accident or something, and he kept producing at almost as fast a pace as he did before. But even after he lost the vision in the second eye and was totally blind, he had a photographic memory, and he had someone doing his writing for him, and he told him what to write. He saw all these equations in his head, and he had this person. I can't imagine what it would be like being his secretary, because he was just driving them, over and over. I mean, hundreds of publications, many of those after he was totally blind. Incredible mind. I can't remember if it's his story or Gauss's. I always get those two crossed up for some reason. That when he was a very young child, he was just watching his dad, I think was an accountant, this may have been Gauss, do some paper, book work, accounting work, and said, "Dad, you made a mistake there." I mean, he hadn't even been to school yet. He was like 5 years old or something, and he found an error in what his dad was doing. He was an incredible mind. Okay, whether that was Gauss or not, I don't know. All right, but anyway, Euler. Okay, so to generalize the procedures we just illustrated, we use the linearization of the unknown solution, y of x, at the point x equal x0. So that's the first thing we did. Okay, I was reaching for my mouse. Okay, that was the first thing we did. We put x0, and here's your f of x, 0, y0. We put that in there. Okay, that's how we calculated our slope at the point x0, y0. So that's exact. Y0 was exact. X0 was exact. That was basically our point slope formula we just talked about. This is the y minus y0 is equal to m times x minus x0. Same thing. We just rearranged it. Now, right here, that gave us this slope, this line here, and we went from x0 to x1, which was the h now. That's why I said this is called the step size. We went up by 0.1. Okay, now at 0.1 you would go to 2.1. Okay, now at 2.1 what we do, okay, we let x be a usually small positive increment in the x-axis, okay? Replacing x by x plus x0 plus h. That's a lot easier than it seems. That's x0 is 2, h was 0.1, so the x1 now becomes 2.1. We get this new linear approximation. This is your y1 is equal y0, which was 4, plus the slope 1.8 times x0 plus 4 plus 0.1. That would be that would be 4.1 minus 4, so that's 0.1. Okay, so your y1 is then simply y0 plus your step size times the slope at the new point, x1, y1. Okay, now remember what we did. We picked an x1, 2.1 say. We plugged that in here. Wait, here comes Dawson. So let me get Dawson here. I can't write with my Wacom ionizing pen, so let me write with a real one. Okay, there's Dawson. And again, of course, when I need it, the pen doesn't write. Okay. All right, so Dawson's here. So we're only missing Corbin and Ricky. Now, I think most of you were here before, and when Ricky told us this, so I don't feel like I'm speaking out of turn. Ricky's dad has come down with COVID-19, and she's having to be his caretaker, which is unfortunate. The reason is her grandfather had been sick and in the hospital. Her mother was taking care of him, and her dad had been helping her mom take care of him before he got sick. And then he got sick. The grandfather was getting better. I think he had been in the hospital. He came home. It was nothing to do with COVID-19. So the granddad came home. His mom was still helping, and his dad was helping get him home, all that kind of stuff. Then within a day or two of that, her dad started having symptoms. And these were symptoms of COVID-19. He was tested and sure enough has it. So he has COVID-19. Now the grandfather has now started having symptoms. I don't know how that's turned out. I think he's gone back to the hospital. Being much older, that's risky. I haven't heard whether he actually had it or not, but the mother's taking care of the grandfather, so Ricky is having to take care of the father. So she's trying to stay as safe as possible, and so far, she emailed yesterday and it sounded like everything was still okay. She's trying to keep up with things with the YouTube videos and stuff, so tough row to hoe there, but we may or may not see Ricky today, but that's why things are like they are. All right, so let's go back to this. What we had here, when you increase the increment, the x by x plus h, and then, or x0 plus h, and then subtract x0, you just have an h there. So here's Euler's method. Your first approximation, L of x1, is your first previous approximation, which this was exact then, 4, plus the increment, 0.1, times f of, not f that we had before, but f of the new approximation. Now, problem with this is we don't know what the y1 is. I think they've got the numbering off just a little bit here. In fact, they do. This should be reading x0, y0, okay? Because you see, that's f of x0, y0 times h. Okay, so they misprinted this. That should be x0, y0. Okay. Now, the y1 is L of x0, which is right what this was. And the point x1, y1 is then put back into your tangent expression, the f, to get your new slope at that new value. okay? And then you just move on from there. Of course, the accuracy of the approximation, as always, depends on the sample size. It also depends on how the curve's behaving. If you can imagine up here, okay, you make an approximation here, it's going to get you further off, and then the next approximation is going to get you further off. So when the curve is doing a lot of drastic behavior here, this is going to be pretty bad. When it's on a relatively straight stretch, your approximation's going to be a little bit better. Okay, so they're not going into that, but it's reality. So we usually choose the H, as I said, as a step side to be what they call reasonably small. That's like reasonably close. I mean, what is reasonably small? We don't know. Up here, you better use a tiny step size to try to keep up with this curve as it's changing rapidly. Down here, the step size, like right in here, where that's almost linear, your step size could be a little bigger, but since you're using, so anyway, it varies, okay? So let's move on. That gave you your regression formula. This is it here. Well, they're going to get to it in a minute. So your y of x2, which I would call y2, is equal to y of x1, and why they didn't, well, x2 would be x0 plus h, plus 2h. Why? Because it would be x1 plus h, but x1 was x0 plus h. So that's why they put it here. Not the way you would normally write it, but it would be okay. So that would be, and here they said it, x1 plus h, and that gives you a new y2, an approximate y2, and that would be y1 plus h times. And see, this time is right. This one should have been an x0, y0. This is an x1, y1. Okay. Now, continuing that, here's your recursive formula. Notice what we got. Yeah, get out of there. Let me scoot it on up so I don't trigger that. Okay. So notice what we got. Y plus 1, this would be our y2, would be y sub n, this is n plus 1, is y sub n plus h, your step size, times f, that function you know already, okay, at xn, yn. So basically you use what you did last time to get the new one, and then calculate the new one and use it to get the next one, okay? And this is x sub n is x sub n minus 1 plus h. I don't know why they go back to say x0 plus nh. So much easier just do x sub n minus 1 plus h. That procedure is using successive tangent lines is called Euler's method. Okay, so let's do one with a problem. And it's going to be that same problem we've had. So there's your initial value problem, just like we had it. We'll use Euler's method to obtain an approximate solution to y of 2.5. We know y of 2, and we're first going to use h equal 0.1, then we'll come back and do h equal 0.05, a smaller step size. Now, smaller step size will sure enough give us a better answer, but it takes twice as long to do, because you have to go through this whole process twice as long to get from 2 to 2.5 as if you did step side of 0.1. Okay, now here's the formula. Let's go back and to our whiteboard, which is where we're doing it. So we got our y1 here. Okay, now let's do what we got to do. Okay, first your x1, and I have actually written it down, so I'll write it down. And now I'm writing with my finger again rather than with the board. I'm Got so used to doing that. Okay, x one is equal to x0 plus 1, so that's going to be 2.1. Okay, now let's also figure out what your f of x1 y1 is. Yuck, there, I just did it. Yeah. Again, I'm near the top of the board, so I tend to hit these control keys. I don't know if you can see those. And I don't know what they do yet, except they get in the way, okay? Because I tend to rest when I write like this, I rest my fist on that, and I've got to learn not to do that. But it's hard to write without doing it. As you can see, this is almost as bad as with my right finger. We have to figure out what that slope is, f of x1, y1. Well, the x1, y1, I should have written it down, but yeah, get out of there. Okay. This is f of 2.1, comma, 4.18, because that was your y1. Okay. Here's your F formula. What am I? Oh, my calculator. Your F formula is here. Let's write the recursive relation. Okay, let's write that. Not on the screen. Okay, yeah. I'll get this down in a bit. No, it'll be a while. Okay. I don't know why I keep getting these messages here. But this is y sub, and there we go to doing that again. Now, I don't know what alt group means. I wish I could undo that. Y sub 2 would be y sub 1 plus h times f sub f of, I probably shouldn't put that parentheses in there, x1 y1. Okay, so let me take out this parenthesis. Oh, I'm not good at this. Okay, so what we have to do is calculate f of 2.1, 4.18. Well, here is your f. This is, yuck. This is, I keep forgetting that. This is your f right here. Okay, so we're going to plug in for y 4.18 and for x 2.1. And we're going to get our new slope there. Okay, it's just so hard to write. So pull out your calculator. Okay, so your new f, your new slope, is going to be 0.1 times the square root of 4.18. So on my phone I have to do 4.18, and then I have to hit the square root key. Okay, and then add to that 0.4 times 2.1 squared, and then press an equal. So our new slope, the last one was 1.8, the new slope is 1.96. So this is, writing on the wrong screen. This is, I'm going to have to write it here because I think this is, again, here we go again doing that mess. Okay. This is equal to 1.96 blah blah blah. I haven't figured out why it does that yet. I haven't figured out. It's really closer to 1.97. I can't get it to write. 1.9. See, it just won't write. And it's something about either the way I'm holding the pen or something. 1.96845. That's what I got. There's a 0 after that, so I'll stop there. Okay, that's your F that's down here. That's that F right there. So I'm going to multiply that F that I just calculated times 0.1. That's our step size, 0.1. And then add to that our Y1, which was 4.18, equal, there's our Y2. The Y2 that I got then was, let me write it here, and again, equal to 4.376845. I don't know why we wound up with another 4.5, but we did. Okay. I don't know if you're doing it on your calculator, but that's what I got for my Y2. Okay. Now I also need to note what my X2 is. So X sub 2, this is the easy one, is equal to X sub 1, which is 2.1, plus 0.1. That's your step size. So that's 2.2. And there we went and did that again. 2.1. Not 2.2. Okay. So now what do we do? Calculate your new slope. The slope at x1, y1 is at 2.2. And then that value for y, right here, the 4.376845. Okay, we have to calculate that again. Okay. Okay. So that F again is this thing right over here, right there. So I've got my y there, 4.37. I'm going to go on and take a square root of it. Okay, first let me look in the book and make sure they're progressing the same way I am. Their y2 was 4.3768. 4.3768, right. Okay, so I'm going to take this 4.3768, but I'm leaving all the digits on there for now, okay, and take the square root of it, okay, and multiply that by 0.1 and add to that 0.4 times, and my new x2 is 2.2 squared, and hit an equal sign. Okay, now my new y2 is now, no, my new f is now 2.1452. So this, get on the right screen here. Okay, that's supposed to be a 2.1452. I know that's ugly. That's my new f. Okay, so what's your next value? Your y3 is equal to y2, which was that thing there. I'm just going to write down y2. This one right up here. Wait, no. Yeah, that's your y2, the 4.3768. y2 plus h, which is 0.1, times this f that we just did. So I'm going to not write it all down. I'll just put that. And here we go again. Okay, so the y, so this f that I've got on my screen right now, 2.1452 blah 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 blah, is going to multiply times 0.1 and add to that the y2. Now I don't have all the digits anymore. I could have saved them, I guess, but I didn't. 4.376845, and press equal, and there's our new y3. Okay, this y3 would then be 4.59 1366, I'm going to call it. I don't need that many digits, but that's what I got. Let's see if we agree. Our y3 is 4.5914. They rounded a little earlier than I did. Do you see how this procedure works? Any questions about it? Okay, it's mostly just bookkeeping, okay? And my bookkeeping is sort of sloppy here because the writing is really bad. Now, if you notice in the book, and let's go back to the book. Can I stop this now, or do you want to see it done another step or two? Up to you. Anybody? Say that again.
Could you show us the additional one that you sent?
Okay, say that one more time. You want to do one more? Is that what you said?
Yes, sir.
Okay, right. So the next one is going to be, we've figured out what y3 is. Okay. Now we also have to document what x3 is. That's the easy one. I can do that one. The x2 was 2.2. x3 is 2.3. That was easy. We also need to know what your next f is. And I'm going to call that f3 so I can keep up with. There it goes again. Okay, I'm going to call this f sub 3. That's pretty ugly, but it's f sub 3. And that's equal to, you plug in to this function over here. If I can get the thing to show, this one right here, you plug in your y3, which is 4.591366, and your x3, which is 2.3. So the f sub 3 of those two values, I'm not writing them down, that would be 2.3 for the x3, that would be easy, and the y3 would be this one here. So I'm going to plug that into this equation here. Okay, the y in there, the x in there, and that's my new f3, I'm going to call it. Okay, so I'm going to do that with my calculator. Okay, I've got in there my y3, so while I've got it in there, I'm going to take the square root of it. Okay, and then multiply that by 0.1, just like it shows up here. Okay, and then add to that 0.4 times, and then my x3, which is 2.3 squared, and then press my equal, and I get my new f sub 3 to be something on the order of 2.33. I ran into a zero, so I'm going to stop right there. Okay, 2.33. That's my f sub 3. So now we're ready to calculate our new y4. y4 is equal to y3, which was our 4.59 blah 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 blah, okay, plus, this is your recursion formula that we have right up here, 0.1, that was our h. That's supposed to be a 0.1, and why it does those things, I don't know. I must be hitting it too hard, too soft, I don't know. Double striking, I don't know. And then we put in this new f here, which was the 2.33. There it did it again. Okay, that I try to point. There's your new f. Okay, all right. So with my calculator, since I got that f in there, I'm going to multiply that by 0.1 times 0.1 plus 4.59. I'll write out all those digits. 4.591366 equal, and my new y4 keep wanting to write on the screen like I used to, 4.82, excuse me, sorry I didn't move the mic in time. Did that blow your ears out? Okay, sorry about that. 4.82, come on down, okay, 8244. Okay, how did they go for y4? 4.8244. Yeah, we got it. Do you see how that works? What you go next is y4 is just 2.4, and then you calculate your f4, which is plugging in that y4 and the new x4 into this formula here. That's your new f4, and then you go through. Now, as you can see by the way I've been doing it using the number I just had on my screen, this can be programmed in a computer relatively easily. Okay, you don't have to have great programming skills to do this. You can do it, and Euler's method, I'm sure, has been done that way many times over. It's tedious when you're doing it by hand, even more tedious when you're doing it on a screen, you know, that's not writing very well, but you get it. And what they did, just let's go. Okay, you need to see another step. I'll be glad to do it if any of you need that next step. Yay or nay?
I don't think I need it, but can you keep the stuff on the screen? I had to finish copying it now.
Okay, all right. And sorry that I didn't write all the numbers down, the digits down, but I just got tired, and I hope you can read that this thing right here is a 0.1. I put the point there, I went to write the 1, I picked up the pen, but see, I can't even get the pen to move now. It's sort of like there's a sticky place on the screen there. That's a 0.1, that's a 0.3. Again, I put a point there, I went to write the 3, and it connected the 2 for some mysterious reason, and see, it got hung up again there. Okay, so anyway, it did the same thing over here with the 1.8. I picked up the pen and went to write the X, and it drew a line between the two. I don't know why it does that. I will try to, as I get better at it, maybe I can eliminate it, but so far I haven't even figured out why it does it. Remember your F. Every time you want to do an F, you go back to this formula here. Use the last y sub n and x. See, again, it's not moving and then it jumps. X sub n, you put those in there and get your new, what I've been calling F sub n. I don't know if the book uses that terminology, but it makes sense to me. Okay, so every time you get a new y, figure out what the new x, that's easy. Then go back and use those two new ones to get your new f using your differential equation, because that is your f of xy. Okay, and then once you get that, then plug it into the regression formula that I never did write it down. I probably should have. Let me write it right up here if I can get it to write. Y sub n is equal to y sub n minus 1 plus h times, there I put the times there again, what I call f sub n minus 1 of x, there it went and did that again, yuck, of x sub n minus 1 y sub n minus 1. I can't figure out why it does that. Just every time. Okay, so ooh, that's too much, but anyway, that's your regression formula, so to speak. Now they may have written it, yeah, they wrote it the other way. Y sub n plus 1 is equal to y sub n plus h times f sub n, that would be easier to write, calculated at x sub n, y sub n. That would have been easier to write. So perhaps I should have done it that way. I'll do it that way down here. I don't know if it'll be any easier to read, but f sub n, no, yuck. There we go. This is y sub n plus 1. Is equal to y sub n plus h times f sub n evaluated at x sub n. I'm writing what I'm thinking, not what I'm saying. I was thinking of the next step. Okay. Okay. I don't know what it's doing here, why it's doing it that way. It took the y and wrote it backwards. Okay. X sub n, y sub n. There it goes again. Okay, there's your regression formula. So every time, what you did the last time gave you your y sub n plus 1. To get your new x sub n plus 1, just add point whatever your h to it, okay? And then to get the f of n plus 1, you plug in that x plus 1 and y sub n plus 1 and calculate that, multiply it by h, and then add it to the previous y. That gives you the next y, and go on from there. Okay. It's just mostly bookkeeping, keeping things in order, keeping up with what's what, you know, and plugging them in at the right places. All right, there. Do I need to do any more with that? Again, it's fairly tedious. Oh, I was moving on my screen and there was nothing to move. Okay, so let's go back to, oh, were you through, Melissa? I didn't ask. Okay, good. All right, so let's go back here and see what we got. And sure enough, our y's were coming up really close to what theirs were. We got up to 2.4. We didn't do 2.5, but you get 2.5 by doing x sub x, or 2.4 plus h times this, the f that you get by plugging in this and that into this formula right here. Okay, now, and then that gives you your your y sub 5, and your x of 5 just went to that. Now, if you move on down here, now this is interesting. Look at that. In your text, if you got a book open, that's supposed to be h is equal to 0.1. And that's all messed up. Now, some of you have the ebook or the PDF that, because you sent it to me, your book doesn't say that. It says 0.1, 0.1. This one's supposed to be 0.05, and yet they messed that up. The PDF obviously didn't communicate that well. So if you want to do, now let me see if my Wacom will write on that. Okay, I don't see that it will, and I can't get a pen to do it, so it doesn't look like I can write on that. On a PowerPoint I can write, but not on a PDF, obviously. So that's a 0.1 right there. This down here is a 0.05. Okay, and notice they start the same, but the ones to compare are this one, 2.1, to this 2.1, which took 2 steps to get here, 1 step up there. You got 1.1842, which is a little bit greater than what this one was. But if you look back here at your, well, sorry, maybe I better do it this way. This is going to move too much, too fast. Yeah, if you look back here, you see this is underestimating the curve. Okay? Now, by doing smaller steps, you get closer to it. You're still not on it, but you're at least closer. Okay? And let me move this back down here. And that's why this one at 2.1 gets you closer to the curve. And then at 2.2, this was 4.3768. At 2.2 is 4.3854. That's closer to the curve. It's still not on the curve, but it's closer. 2.3 was 4.6045. Up here it was 4.5914. So you see you are closer to the curve, but you're still not on it. Your 5 here was 2.5 was 5.0997. Here was 0.768. Now, to 2 decimal places, it's the same. They would both be a 5.1. But this one is closer to 5.1. Okay. Now, I don't believe they know exactly what the value is, so we can't compare it to the real value. But in example 2, we apply Euler's method to a differential equation, which we know the solution. So we can compare this to the approximations that we're getting at each step with the true and the actual values of the initial value problem. So are you ready to go on to 2.2? Alright, now we're almost, what is making that noise? It's not my phone. Okay, it must be something outside. Alright, see, it's 9:52. We go to 10:45. Is it okay to take a quick bladder break now? Anyone have an objection? Okay, so let's go down and we will come back to this place right here. Okay, so I'm going to pause. Okay, now with all this stuff open here, I've lost my screencast-o-matic. So I don't know if I can pause it or not. Let me see what clicking on this does. Nothing. See what clicking on that does. Nothing. Now I did get it started. Let's see what clicking on this does. Nothing. So I don't know if I can pause it or not. So it may just have some dead time here. I don't know why it disappears. I guess I got too many other things open. So I'm going to go on and minimize this again. So I can't pause this. So for people listening, there's going to be a little bit of dead time here while I go take a bladder break. Be right back. All right, I'm back. It takes me a little bit to get everything wired back in place. And sorry I couldn't pause the recording, but that was some dead time. So, any questions then on example 1, ready to move to example 2? Now, if my memory's right, this may have been one of the first problems we looked at. We looked at so many, I can't say for sure, but consider the initial value problem. Y prime is equal to 0.2 xy. Okay, that is certainly a separable equation. This is something we know exactly how to solve. Okay, and we'll solve it if you want to. And it says use Euler's method to obtain approximation, and your initial value is y of 1 is equal to 1. Okay, and to obtain an initial approximation of y of 1.5, and again using h of 0.1 and h of 0.05. Now you see, when you do use a computer to do this, you can make your step size just as small as you want. Again, you'll never get an exact answer, but you'll get closer approximations. Of course, it's going to take more computer time to do so. So if you're running on a big expensive machine and you're taking more CPU time, you're going to get charged for it. But if you got a calculator, and it just depends on, I mean, a laptop that you're programming and stuff, it may take you a bit longer to do it, but you can do it. All right. So there is your function, 0.2 times this. Okay, first, do you want to actually solve this differential equation to see what the answer is when x is 1.5? Do you want to see that or not? Or are y'all confident you know how to do the differential equation? Let me know. I'll be glad to do it if you want to. Anybody? Hello? Can anyone hear me? I can't hear you. Oh, it did cut out? Okay, do you want me to actually solve this using separation of variables? It's fairly easy to do. I'll be glad to do that. Do you want to see that, or are y'all confident you can do that yourselves, or would you just like to see me do it again? Okay, someone said something, but I can't make it out. Okay, did someone say, can I just do it? I don't know why. Okay, good. All right, it's fading. Okay, so let's go to the whiteboard. And is it going to be okay to erase this on the whiteboard now? Ooh, that's ugly, isn't it? Can I erase? Yes? Okay. All right. Now, let me get it in my lap so I copied the problem down right. Okay, here's it is. Now I'm going to write it slightly differently. dy dx. Here I am writing with my finger and not with my stylus. Okay. dy dx. And again, it does that weird thing sometimes. dy dx is equal to 0.2 xy. And with the initial condition that y of 1 is equal to 1. There. It doesn't like equal signs for some reason. I must be doing too fast, too slow, too hard. I don't know. Okay. So how do we do this? We write it in differential form. dy is equal to 0.2 xy dx. When you're doing separation of variables, that's usually the first step. Now we got our x's all on one side, but we got one y hidden over here, so let's take this y and divide it out and move it back there. Okay, so now our differential equation is dy over y. There, it wouldn't write and then went to that thing. Okay, let's go back and see if I can get it right again. dy over y, that's an ugly y, is equal to 0.2 x dx. See, sometimes it'll write, sometimes it won't. Okay, I'm still learning it. Okay, what do we do at this point? Integrate both sides. Okay, I'll put my 0.2 outside the thing there. What is the antiderivative of dy over y? Natural log of absolute value y. Okay, this will be a 0.2, and the antiderivative of x dx is just x squared over 2. And then we've got our plus c here. All right, now this 2 here will cancel in and make this a 0.1. Okay, and by the way, I think I want to write this as maybe a log c rather than a c. That's ugly, but I hope you understand. It's just a constant. Okay, so what do we have here? We have log. Yuck. Sometimes I do that. I don't know why. I go to write log, it becomes an H, and it's just not an H. Okay. Nope. Okay. I think I'm writing the L and the N at the same time. I don't know. So this is log of y. I'll try to keep the absolute value bars. It's easier now than it was before. Okay, and this will be 0.1, because I can't read my writing too well, x squared plus log c. Okay, so let's subtract the log c from both sides. Okay, and move it over here and make this log y plus log c. Okay, I changed signs on it, by the way. Forgive me that. Okay, make this a minus log c here, and then we're adding it. Okay, I want it plus. Okay, is equal to 0.1 x squared. And again, sometimes it writes and sometimes it doesn't. Okay, so I'm going to change this and make it c, the log of c times, I think I should have done it the other way. Sorry. Let's make this e to the c plus e to the c. And then this would have been 0.1 I'm trying to get too fancy with it. Yeah, this would be log of c times y. Let me go on down and write it the way I was doing to c times y is equal to, again, the equal sign doesn't do well, 0.1 x squared. Okay, now we e both sides, and that produces a cy is equal to e to the 0.1 x squared. Okay, now we're going to plug in our initial conditions. When y is equal to 1, this gives us c is equal to e to the 0.1, because when x equal 1, that's that. So our c here would then be e to the 0.1 is equal to, y is equal to e to the 0.1 x squared. And again, I don't know why. Sometimes it writes and sometimes it doesn't. Okay, so to solve for y, this would be y is equal to, again, the equal signs don't do well, is equal to, if you divide both sides by e to the 0.1, you're going to wind up with e to the 0.1, I don't know if I wrote it the best way possible, x squared over e to the 0.1. Now let's see. You could then write that, sorry about this, I chose a silly way to do it, but still is doable. This is the same as e to the 0.1 x squared minus 0.1, which they then wrote as e to the 0.1 times x squared minus 1. Okay. Yeah, that's what we got. Now in the book they did say verify that as a solution. We've shown it's a solution because we worked it out. Okay. So there is your solution to your differential equation. This one we know that solution. Okay. So hang on to that thought. I'm going to have to erase to be able to write what we need to, but that's going to be your that is the actual solution. So let's go back now. I think can I clear all this, or are you still writing? Anybody? Okay, so let's clear. Oh, can't get my cursor to move. I could have used my pen, but it's easier with my finger here. Okay, so let's repose our problem here. Y prime is equal to 0.2. There it went and did that again, xy, with initial condition of y of 1 is equal to 1. Okay. Now, use Euler's method to obtain an approximation to y of 1.5. Now, we didn't do that with our real solution. We'll go back and do that later. We'll use first h is equal to 0.1. Okay, so let's go here and we'll do h is equal to 0.1. Okay, so this, by the way, is your f of xy now, 0.2 times xy. Okay, now if I can get my, okay, so your y sub 0 is equal to 1, your x sub 0 is equal to 1, and what I've been calling your f of sub 0 would then be f of 1 comma 1, which would be, yuck. Okay, it's going to fade away in a minute. I don't know what that key does, but it doesn't seem to hurt anything, I hope, anyway. Okay, let me get back here. And what is this? This is plug in 1 and 1 here, and you simply get 0.2. Everybody see that? Okay. You plug in over here, x equal 1, y is equal 1, you get a 0.2. Okay. So with this in mind, let's get our first approximation. Y sub 1 is equal to y sub 0, which is 1, plus your h, which is 0.1, times your f of 1, 1, f sub 0 of 1, 1, which is 0.2. So your y1 is 1.02, because 0.1 times 0.2 is 0.02, so there's your y1. Okay? Is 1.02, exactly. Okay? Now, your x sub 1, to go with that y sub 1, is now 1.1, 1 plus h, x sub 0 plus h. Okay? Now we have to calculate what our f sub 1 is. And that's the f when you plug in your x value, which is 1.1, there that again, and your y value, which is 1.02. Okay? And that will be, okay, 0.2 times 1.1 times 1.02. Yeah, I did it again. 1.02. Okay. Pull out the handy dandy calculator and see what that gives us. You're probably way ahead of me, especially by the time I get the phone turned on. Okay, 0.2. Yuck. 0.2 times 1.1 times 1.02. And that was a 0.2244. Yeah, that makes sense. It's pretty close to what it was before. It was 0.2 before. Now it's a 0.2244. All right. So your y sub 2 is equal to y sub 1, which was 1.02, plus your h. Does it help for me to write down that recursive formula? Let me go up here and do it. Y sub n, yuck. Why it does that, I don't know. It gets hung up and won't do. Y sub n plus 1 is equal to y sub n. There, it did it again. Must be how I write my n's. N plus h times, I didn't mean to put that, x sub n, which is f calculated x sub n y sub n. Okay, that's what we do. So our y sub 1 was 1.02, your h was 0.1, 0.1, and then your f sub h, f sub 1, we just calculated here, was your 0.2244. Again, it writes sometimes and it doesn't write other times. Okay, so the 0.2244 I've still got on my calculator. First I'm going to multiply that by 0.1 and then add to that 1.02. Alright, this time I got my y sub 2 to be 1.04 244. Okay, and let's see what they got their y sub 2 to be. I'm on the wrong page. 1.0424. We carried one extra digit. Okay, so since we've got that, let's go on and figure out what our x sub 2 is. Since we got y sub 2, x sub 2 would then be 1.2. Okay, again, it did that same strange thing there. And then we're going to have to calculate our f sub 2. Okay, and the f sub 2 evaluated at x sub 2, y sub 2, plugging in up here, it's your, I've got the y sub 2 on my screen right now, 1.042244 times 0.2 times 1.2. And that gave me my f sub 2 to be 2.5, which makes sort of sense. 2.501856. You don't need to carry that many digits, but I did. Okay, now we're ready to do our y sub 3. If I could get, I keep forgetting, y sub 3. Okay, that's your y sub 2, which was 1.04 244 plus your h, which is 0.1, times your f, which is 2.5 0 1 8 5 6. Okay, so I've got my, that's a 0 point. Wait a minute, I wrote this wrong. Okay, this decimal is in front and this decimal is in front. Okay, sorry about that. I don't know why I wrote it in scientific notation or something, okay, without the thing. So I'm going to take this value, the 0.2501856, multiply it by 0.1, and add to that 1.04244, and that gives me a 1.06. So my new y3 is 1.06 74 58. It's ridiculous to keep this many digits, but I'm doing it. 56. Okay, in the book they came up with, I'm in the wrong column again, 1.0675. Yeah, okay, so we've got it. So now that we've got our y3, let's go on and do our x3. I like the x's, they're so easy. x3 is 1.3. Okay, now we've got to calculate our f3. Now the book doesn't call it that, I do. It just helps me know. That's where you evaluated x3, which is 1.3, and there it did the same. Oops, there, that was my bad that time. That wasn't the book doing it, the pen doing it. Okay, comma, y3 was 1.06, 7, blah, blah, blah. Okay, and what would that be? Okay, it's that number I have in here, 1.0674, blah, 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 blah. That's your y, multiplied by 0.2 and multiplied by 1.3. So that new f is now 0.27. This time I wrote it right. 7, 7, 5. This time I'm going to round that to a 4. Because it's a 3/9, so I'll do that to a 4. So there's my new F3. You get the pattern? The y sub 4 is miserable writing. Yes, then, okay. The y sub 3, which is your 1.06 that I'll write down later, plus the 0.1 times this number right here. So this number I've got on my screen is going to be multiplied by 0.1 and added to that 1.06 745856 equal, and that gave me my y4. I didn't work out the thing, 1.09 3 or 3 4. Let's round that up. Okay. Now, how'd the book do? Look on the right page. 1.09. Okay. Okay, I must have dropped a digit somewhere there. Sorry. 1.0952. And I must have not entered a digit right when I was entering this number here. So sorry about that. That's a 5.2. I don't know if the rest of them are right or not, but it's a 1.0952 is what the book got. Okay, I'm going to stop there if it's okay, because I made a mistake somewhere. I've got to go back and retrack all that if I'm going to do it. You go on to do at X2, you do your F2, X4, and do your F4, where you plug it, your X4, Y4, back into your F up there, 0.2 times XY. Okay, so they come up with the Y sub 5 I'm copying this from the book. I'm not calculating it. Y sub 5, and again, it won't do an equal sign, is 1.1259. This is from theirs. Okay. Now, let's go back to the solution we got before. That y is equal to e to the 0.1 times x squared minus 1. Okay, now let's evaluate that. Okay, time out just a moment. Okay, when x equal 1, this thing right here is a 0, and e to the 0 is 1. So our initial condition does match this. I should have done that way back then. But now we're doing y at x equal 1.5. That aggravates the fool out of me. Okay. 1.5, and this time there it did the strange thing with that again. So we're going to do 1.5, square it, subtract 1 from it. Okay, I got a 1.25. I'm going to take the exponential of that. Okay, that's a 3.49. No, sorry, I botched it. Start over. 1.5, square it, subtract 1 from it, equal, multiply that by 0.1. I forgot that step. Equal, that's 0.125. Take the e of that, and that gives me a 1.13. 1.133148445 3. That's way more digits than you need. Okay, this is the actual value. This down here is our estimated value. So we're off by less than 0.01. Okay, so our absolute error was 0.0073. Not bad. The relative error is you take that absolute error okay, which is the actual value, this one, minus the calculated value that gives you your error, divided by the actual value. So if we do that, I'm going to just use the numbers I have here, 1.13 blah 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 minus 1.1259 1.1259 equal, that's the absolute error, 0.00272, I think it is. They got 7.3, I'm not sure. Well, they rounded more than I did, okay? And then take that and divide it by the actual value, which is a 1.133148453 equal, and that in percent is 0.64%, which is still pretty small, 0.0063 or 0064. That is a fairly small absolute error, okay? But if you had used the smaller increment, 0.05, the h of 0.05, without doing this in the book, that gave you an absolute error of about half of what our other absolute value was, absolute error was, and that gave us a relative percent of about half of what this one is. So if you see the table in the book, you see they do work out that way. Now it's a long and grinding road to get there, and to do all those 0.05s, all those steps. It's 10 steps to get from 1 to 1.5 when you're doing 0.05, and you have to keep up with the digits, and you have to not make any. When I'm punching in on my telephone, those numbers are so small and my fingers are so fat, quite often it either won't register or the number next to it registers too, or something like that. So I have to be very, very careful when I'm doing this on a telephone. Okay, but that's pretty much, hopefully. Does anyone need to see any of this done any further? The 0.05 or anything else? Do you get the procedure down? Okay, if not, let's go back to, and I started to do it on my Wacom, can't do it there. Go back here. Okay, let's go back to this. Okay, now scrolling down, here's the table, and again they have so much trouble with this h. This is h is equal to 0.1, this h is equal to 0.05. I don't know what's wrong with the graphics people there, but they have some problems, okay? And do y'all see this orange bar in the middle of things here? Is that messing up on your screen, or is it only on mine? Now it's fading out. Well, not a serious thing, but the actual value 1.1331 in both cases here, and they do the actual value at every step of the way. Every one of these values, every one of those values. And you see your absolute error, of course, the first time is right on the money. Relative error, right on the money. But as the more you go, the more this increases, the absolute error and the relative error. But on the 0.05s, look how slowly they take off. Here it was half of this. Starting off here, it's a quarter of that. So again, with smaller increments closer to the original, you get very, very good thing. This is a percent, remember, that's 0.0003. So you're a really good approximation here. Down till you get 1.5, you're getting far enough away from your original, you are introducing a bit more error. Okay? Now, this course is not dealing with relative error, percentage relative error, and that kind of stuff. Hopefully you know that already, but that's what they're using here. The relative error is your absolute error, which is the actual, no, It should really be the measured minus the actual is really what absolute error is. But then you divide it by an absolute value anyway, so I think they put the absolute value in the wrong place. It should really be on top because the actual value is not is positive here. The absolute error, I think they have the absolute value bars in the wrong place. But anyway, that's why they call it absolute. The error in a positive sense divided by the value in a positive sense, and that the relative error is this, and the percentage relative error is you write it as a percent. Okay, they didn't write the percent. They didn't write the relative error. They just wrote the percent relative error in both cases. Okay, you just move your decimal 2 more places to the left. Okay. Now, they do a little caveat here. Euler's method is just one of many different ways to in which a solution of a differential equation can be approximated. Although it's attractive for its simplicity, it's seldom used in serious calculations because you can't get very far from your initial value before you start going into larger errors, like you just saw. This is introduced here just to give you a first taste of numerical methods. We'll go into greater detail in Chapter 9 when you start talking about the 4th order Runge-Kutta method. Now, we're not going to get there. Sorry about that, but they've shortened our summer term. We're not going to come close, okay? That's also called the RK4 method. That's covered in Chapter 9. It's a better approach. Again, it's an approximation, but not an exact. Then they talk about number solvers, numerical solvers. That's actually what I bet you're going to have at your place of business, okay? Because guess what? A differential equation, especially first order, dy dx, that's change of y over change of x, you can choose your x to be as small as your delta x as small as you want to and calculate your delta y's. Computers do it. Those are your numerical solvers. That's what you're going to be probably using, some sort of software package that's generated to produce these numerical approximations. You're not going to use Euler. You probably won't even be using Runge-Kutta. But by the way, here's 2 more names. Who in the world was Runge? Who in the world was Kutta? Okay. How did they develop this? What did one develop the other? There's several potential paper topics there. Okay. We're not going to into it, but I think they do show a graph. Yes, here was one. This one that we just did, e to the, our solution was what we had. Here is the actual solution, is the blue curve. Euler's method goes up in increments to here, and you see we were pretty far off here by the time we got to 4. Now, of course, we didn't even come close to 4. We started at 1, 1. Okay, this may have been a different... No, this is that one. Okay. Doesn't look like we started at 1, 1. That should have been right on the curve. But by the time we got to 2, which we didn't get, we just went to 1.5. And we were still pretty close. But this is... oh, wait. I don't know. They're not saying what your step size. Oh, this I think was 0.1. Okay. Now, Runge-Kutta, when you use h of 1, you produce this. Well, if you notice what Runge-Kutta is doing, it's actually mapping it to the exact value at those increments of 1, 2, 3, 4, and then doing basically a linear approximation between the two. Well, you would have to know the exact solution to do that. So there are ways to do that otherwise. But you see, RK4 gets you closer generally, and you'll do. So then they go back to using a numerical solver. And basically what you're doing, and this is their warning. Sometimes using those, you'll get wacko things like this. Obviously, that's not the function you're looking for. That is a problem when you're doing step sizes. If you happen to get one that reverberates an error, is how I call it, that's not a real technical term, then you get something wacko like this. This is something I'm guessing came in at maybe 0 on this side and 1 or 5 on this side or something like that, and this one gave you a completely weird solution. Okay, and that's because you happen to hit on a resonant frequency that just completely threw you off. Okay, so you have to watch out for those numerical solver. They're approximations, and sometimes their approximation stinks. All right, that finished 2.6. Here's homework exercises. Do number 1 if that's in the back of the book. Do number 3 if it's in the back of the book. Do any of the odds 5 through 9 if they're in the back of the book. Do 11 if it's in the back of the book. And that's all. Okay. Now, we're not going into that's the end of the section 2. Chapter 2 in review. If you feel like you need more problems to work on, all these odd ones are in the back of the book, so you can do those, or at least some of them are. Selected odd number problems are in the back, so you can do any of 1 through 11 if you choose to. That's sort of fill in the blank. Then you could do, let's see, where's 12? Oh, there was 13. Wait, 12 is even. Okay. You can do 13. It should be in the back of the book. You can do 15. It should be in the back of the book. You can do 17. It should be in the back of the book. Okay. You can do any of the odds 19 to 25. They should be in the back of the book. You can do either 27 or 29. 29 is at the top of the next column here. Whoops, too much. I can't use that to progress here. Oh, here we go. There was 29 right there. It wasn't as bad as I thought. Yuck. There was 29. Okay. You can do 31 if it's in the back of the book. Whoa. It just takes off and goes on its own. It's doing some strange things here. I think it's because Melissa's in the way. Melissa, get out of the way here. Okay. Yeah. Okay. So let's go back down here and see if we can do this. Okay. 29 if it's in the back, 31 if it's in the back. That's one of those piecewise defined functions. 34 if it's in the back, 33 if it's in the back, 35 or 37 if they're in the back, 39 if it's in the back, and that's it. Okay. I think that was the last one. Okay, so you got more that you can practice with. You don't have to do those unless you want to. So now we have finished Chapter 2 in its entirety. So your test did cover one Euler method problem, so you weren't expected to start at that part yet, but you could have started over the weekend. I put the test out there. It's a PDF file, so you should be able to do it. It's probably not a great pretty PDF file, but I think it's readable. So do that if you can. Technically, 1 week from today would be when a good target to get it done, but you got plenty of time before we get to the next topic. All right, the next topic in the book is modeling with first order differential equations. Now that sounds like a lot of fun, but we just don't have time, and there was nothing about modeling, I don't think, in the course description. So we're going to skip chapter 3, and we're moving on to chapter 4, which is higher order differential equations, and we'll pick up from there. Notice chapter 2 has already been first order differential equations. So we're moving on to chapter 4, higher order differential equations. Okay, if you take a look at that, there are 10 sections here. Obviously, we're not going to have time to do 10 sections. So we're going to do 4.1, preliminary theory. That's usually sort of a drag. 4.2, reduction of order, because we're going to need that later. And then we'll actually get into the real stuff with 4.3 and then 4.4. 4.4 is one method, superposition. 4.5 is a second method. They suggest you do either one or the other. Unless y'all have a preference, we're probably going to go with superposition. Seems like when I've taught it before, students like or understand that more easily. Then we're going to start running out of time, so we'll try to get 4.5 done if possible. Maybe to 4.6, that's going to be tough. 4.7, and I don't know if we're going to make it to 4.8 or not. So anyway, we're probably going to die in chapter 4. There's so many sections here, and hopefully this is going to give you enough to get you going into your next area of study. Any questions? We've just run out of time. I don't want to keep you any longer. I've got another class starting at 11. Any questions? Now that you've got a test to work on, I'd say focus on the test. If you run into problems on homework, please send them to me. That's absolutely, I think, a great idea to keep sending me problems. If you're running into something and say, hey, I don't know how they got this, by all means send me those. But if you're able to do the homework problems, to keep from having to, whatever you have to do, PDF or pictures or whatever, if that's just a pain in the neck, I'd rather you focus on the test. So no, you don't have to keep doing, unless you run into problems. Yeah.
I've been doing the homework, but I forgot to send them to you, and I didn't know if you still want to.
No, once you start having tests, to me, I'd like you to do that. Now, if you finish a test and we aren't ready for the next one, and you want to send me homework then, that's a great idea, just to let me know you're still keeping up, and to let you know that you're still getting answers like you want them to do. Okay, that's probably a weird answer. Did that answer okay? Okay, good deal. Any other questions? Great question, by the way. All right, if that's the case, then I'm going to stop sharing because I'm tired of sharing. And I'll end the meeting unless there's any other questions. Any of you have one? Not? Well, then we'll see you on Thursday. Okay? Take care. Bye-bye.